try this also if someone in the room or watching this remotely afterwards sees as well, maybe please pay attention. So this is really great. It's really good. Okay, so and of course, yeah, feel free to interrupt or ask questions. So I'll be slightly schematic on some aspect of it, and I'm happy to do more details. Yeah, so I wanted to start with a few words of motivation for this whole thing. Yeah, so this work belongs to, I guess, the broad category of works that have to do with scattering amplitudes. And so yeah, the idea is to revisit relativistic quantum theories through their scattering amplitudes. So this thing can have several virtues. One of them would be to understand better either field or string theories. So by that I mean, so either having a more efficient handle on the dynamics, for instance computing high amplitudes or large multiplicity amplitudes, for instance that has been applied to, well, to the computation of supergravity amplitudes at very high order, or to the computation of gravity wave templates, for instance. And I also think that it helps us, or at least it gives us hints as to how we could redefine what we call interesting theories. So there are some patterns, but there are some constraints we impose on the scattering amplitude of theories we think are useful, for instance, unitarity or locality. But you can ask more. You can ask, for instance, that it has a specific UV behavior, that it has a specific spectrum, or that it has a specific soft limits, and so on. And some of these conditions have been seen to arise in scattering amplitude and then used as a bootstrap condition to find new theories. And for instance, that has been of some use to understand how unique and available string theory can be, for instance. So there's some kind of back and forth communication between these two ideas that allow us to see some structure within field and string theories we understand and try to see how broad in general these patterns are and like this. And in particular, when we study string theories that are well known, we find, and then we look at the scattering amplitudes, we find sometimes some very intriguing structure that are completely, well, that is very hard to see from the Lagrangian perspective or completely hidden from the Lagrangian perspective. And they suggest that there are some things or some aspects of this field and string theory that we don't yet fully understand. And one aspect of it that I wanted to discuss today is what's called the double grouping. So which is it's a field that is maybe 40 years old, that really skyrocketed 10 years ago. And yeah, so the basic idea of this is that it seems that the scattering amplitudes in the bunch of seemingly very different theories can be built from some, well, a small number of universal building blocks. So what I mean by building block is the following. So these building blocks can be of two types. There are the ones which are called of color type, that I will denote as CI, and those which are kinematic type, that I denote as NI. So I'll give explicit examples, but basically CI is made out of the tensors that define the symmetric group of the theory, for instance, structure constants or traces of generators of the algebra. And kinematic objects will be formed of polarization vectors or momentum. And to see how universal, how the limited amount of building blocks can be used to build a huge number of theories, we can start by writing some stepping up to schematically. For instance, we can start from the youngest amplitude. So just the theory of pure units, set interacting. And it's been shown that you can write this amplitude in the following way. Where this I here is a sum over cubic diagrams, formal cubic diagrams. For instance, at 4 points, this diagram would be simply the ST and U channel. So you have for arbitrary multiplicity a generalization of these cubic graphs. This thing will be a color factor of some sort. This will be where you have the momentum for different vectors. And this thing will simply be the propagators that you have in this cubic organization. So okay, so it's not trivial from the beginning that you can create that decomposition. Sorry, something I should have said. Is that, yeah, so those building blocks are restricted to satisfy something very important, which is that they respect the same algebraic properties. So these color factors, so I was saying that they are made out of structure constants or traces of generators of the gate group and so on. So they are restricted because of the Jacobi identity or some other defining relations for gate group to verify some algebraic relations. And it turns out that you can build objects out of polarization tensors and momenta and so on that verify the same algebraic relations. And Young-Mills theory, for instance, can be arranged in a way that is a sum of cubic graphs of objects of that sort, which both verify the same color algebra, despite those ones just being made out of polarization vectors and momenta. Okay, so that's already a very non-trivial fact. That's what's really amazing is that, for instance, you can compute the trade amplitude in general relativity. And it turns out to be written like this. Because it can be expressed like this. Where this ni is the same as that one, which is the reason that sometimes you see the statement that gravity is the square of Young-Mills theory. And this kind of mapping, where given building block can be recycled in order to get a new scattering amplitude, goes way beyond those two theories. So for instance, the theory of finance, the nonlinear sigma model, the theory of interacting Gaussian bosons, can be also written in the same way. So as some kinetic numerator times color numerator over the poles of this cubic decomposition. And you can, for instance, take that guy from the Young-Mills decomposition and that guy from the Payan decomposition and form an object. That object happens to have the appropriate behaviors we call the scattering amplitude, and it happens to be the scattering amplitude of one infantry. You can also do the same kind of squaring as you did here, but starting from the nonlinear sigma model, in which case you will just square that guy, and you'll get the scattering amplitude of a specific scalar theory for a special behavior, which has a specific enhanced flow total symmetry. And you can supersymmetrize that whole business and square super Young-Mills to get supergravities of different. You can square Young-Mills with Young-Mills or different, but to get all the supergravities you know with different amounts of supersymmetry, you can add matter field. You can square Young-Mills coupled to matter fields to get supergravity coupled to tensor to vectors and so on. So all this with a very limited number of building blocks. There's one last thing you could do that I want to write here, which is the different theory of scalars. Has the following expression. So instead of having numerator, the kinematic numerator, you just use pure color. That happens to define a cubic theory of a scalar that I will use repeatedly in the talk. Yeah, so it's a scalar with two color groups that interact with cubic lattice. Okay. Good. So that's right. So something I didn't say. So this decomposition is what's called the color kinetic theory. So the fact that you can find objects with like the same algebra and decompose the scattering amplitude in this way goes under the name of color kinetic theory, and has been pioneered by the work of Berkeley and Johansson in 2009. Okay, so that's the usual, I don't know how usual it is to you, but it's the usual story that goes under the name of lower copy. There are many extensions that are possible. for instance, you can consider taking the poles that show up in this decomposition and turn them into massive poles. That, for instance, is important if you try to fit Kaluza-Klein theory in this whole business, or, for instance, just massive young wheels, or if you want to couple young wheels to massive matter, for instance, there are generalizations which are studied and explored in the direction of introducing massive particles in this business. You can consider how many theories are there that can be fit into this whole business, or how many new class of numerators of this sort exist. So we found there's one for young wheels, there's one for pion theory. So one can keep on looking for new theories that fit into this whole picture. One can wonder whether the color numerators can be generalized. So for instance, in Young theory, you find one set of color factors which are a product of structure constants. So you find, for instance, at 4 points, you find color factors that are like this, so product of structure constant, and at higher motility, you find larger products of that sort. So you could wonder whether, for instance, a fully symmetric object at 4 points can be used as a color factor to find a new kind of algebraic structure. It seems to be, for instance, that these kind of things are useful in supergravity, in particular when you have countercurrents that account for anomalies. Something that is rather important is that you could generalize also the kind of objects that you use. So, for instance, you could hide some momenta in that object, which you called the color factor before. So like distributing the momenta between the numerator and the color factor. And that, for instance, that kind of manipulation is important to get string theories out. So by doing this and using the numerator of Young theory, or super-Young theory, sorry, you can get the open superstring by suitably choosing these kind of objects. And you can, again, recycle those objects and put them into a nominal sigma model now, and there's another object that looks like something you can get from string theory. Good. Okay, so that's kind of, so this shows that there are some sort of general rules that are behind this whole thing, but that like the complete scope of the game is not yet known. There are many aspects that are still being explored, many possibilities that are open, and many theories that keep on entering this kind of map. And in particular, we still don't know, I think, we still don't know deeply why it works. So why this kind of composition exists, and except, so we have a technical understanding of where it comes from, but we still don't know why it works, and like, does it suggest something like way deeper than the theories that we're dealing with, than just this technical aspect that allows us to quickly compute, for instance, in gravity.
Is this specific to 4-point amplitude?
No, it's quadrant, sorry. No, this is to all multiplicities. It's even not just tree level. So this thing has been shown, for instance, this equivalence here has been shown at tree level for Young and gravity, at tree level at all multiplicities. So it's a proved thing. It's a conjectural mapping at loop level. So at loop level, you can do something similar, but then you're going to integrate all the documenta afterwards. So you can decompose the integral in that way. So this has not been found to fail, but it's not been proven either. And so it's meant to hold all root order and all multiplicities. Most of it. But that's most of it remaining a conjecture. So why, the why and the what does it suggest are still like very much open questions. And so it's important to get new perspectives or different perspectives, or just explore better all these relations to understand, try to understand really what the rules of the game are. And today I'll just discuss some specific, I'll take a specific look at these questions by going back to the field theory description. So far this is something that one observes in scattering amplitudes, and that is not natural to observe in Lagrangian, although there are some progress in that direction. So I'll go back to the field description, and I stick to tree level amplitude, so this is the case. So you may wonder why they insist to go back to the field description, despite arguing previously that those structures arise in the study of scattering amplitude and not in Lagrangians. And And the reason is that there are still things to learn, as I try to argue with that description, and since we still don't know the rules of the game, it's important to go back and forth between the different pictures we have of this phenomenon. Yeah.
I think it's maybe more obvious for an insider person, but for an outsider, I still didn't quite catch what is the problem that's being solved, or what's the questions being answered. Is this a classification problem that we're trying to use S-matrix properties, at least of certain theories, to classify theories?
Good. So I think so. It's a bit up to you. I mean, in the sense that whether this kind. So you could demand that you only want to study theories that fall into this class. So that would be. I mean, that's a choice. There are theories that we know of that don't fall into this class. So it does. You can, as your working assumption, you can decide to study those theories. So that's something that people have done, trying to understand what those theories are. Like, do they have remarkable properties, and vice versa, do theories that have some remarkable properties all fit into this description. So that's trying to understand whether this should be bootstrap completion tools, interesting theories, is something that people have pursued. From the technical perspective, you may want to study those theories simply because they allow you to recycle things that you've already computed. So, for instance, people are using a lot the fact that finite computations in gravity are insane. Fluent Feynman diagrams are not amazing, but much better. And so once you've done that computation, you get that computation for free. So from the okay, but for instance, something I haven't said is that if you know this and you're doing this map, you're getting some gravity amplitude. So in particular, you're getting gravity amplitude that has the graviton, the dilaton, and the axion in it. So understanding how you can remove those modes, understanding how you can introduce new kind of interactions, like can you add matter, what kind of matter, can you add non-minimal couplings, what kind of minimal coupling and so on, which may be relevant if you want to study some gravitational system, right? Demand that you understand how you get it from each to this.
So I can think of it as a computational tool.
Yeah, I think
you're trying to get it to apply to more problems.
Yeah, I think the major success of this is at the computational level. So yeah, understanding how far you can go with this is an important question for that. But I think it's also, I mean, because it has some it has this very strict and general structure that relies on some algebraic properties and so on. I think people also have considered that it's just something conceptual that is pointing, right? And that it's not just that you should understand what this thing is telling you. But that's more vague. So some people have connected these to specific soft limits or specific UV behaviors on the amplitude that we very. But that's more, I think that's more like a long-term goal. Yeah, probably makes it less computational.
You said that this double copy thing is proved for the angles in Geo.
Yeah.
And still we don't understand why.
I mean, it depends what you mean by why. I think by the why, I mean.
And the proof is like brute force.
Yeah, exactly. There's something of that sort. I mean, we prove it, right? So we understand what structures. We have relations we know how to prove that imply it, right? So it depends where you put your level of why. If you want to highlight the symmetry that you're responsible for.
There's no manifest description,
yeah.
Right? It's clear.
Yeah, there's no deep principle that would one-line principle that would give you this as now. There are some hardcore relations that happen to the good. Yeah. So so this is mostly motivation. Okay. But okay, I'll try to. So what I'm going to do next is now connect these kind of theories that look like this, and try to understand what the field description of these, the field theory description of these facts is. So the result I'll try to reach today is the following. So I'll study the result and then I'll try to go back to it. Sorry. I'll study two kinds of theories. One is Young-Mills theory plus higher derivative operators. So Young-Mills deformed by operators of higher and higher mass dimension, so that it becomes an effective theory. No. Plus some higher derivative correction we can try to work out. We're going to connect another theory, which I'll call the gauge-biojoint scalar. So let me write the Lagrangian and then I'll tell you why it's the case. So the theory of gluons plus higher derivative operators, and that theory of the scalar, I call it biojoint because it has two symmetry indices which are both in the adjoint of some symmetry group, and it's called gauge because it couples to gluons. So this thing is a covariant derivative that has gluon in it, and it's actually except the cubic coupling, except the gauge coupling, so minimal coupling. This is the theory that led to that cubic amplitude. So that term here has three scalars in it.
Yes, that's going right in the middle. You're on that knob in the middle.
Oh, yeah. Yeah, so this, you have this, in addition to the middle coupling HP, you have this cubic coupling. And this means being the structure constant of the two groups, which this symmetry indices are associated. So those are the two theories I'm going to consider, and I want to show two things. The first is that we're going to connect the equations of motion of the two theories. So the equation of motion of the first theory and its EFT deformations are going to be connected to the equation of motion of the second theories and its EFT deformation. And that will result in amplitude relations, which to my knowledge are quite hard to see otherwise. So some amplitudes of pure gluons expressed as a sum of, so amplitudes computing in that theory of pure gluons will be expressed as a sum of amplitudes in the gauge-biojoint scalar theory plus EFT formations of amplitudes which have both gluons and scalars. So there's a sum here that defines what are exactly the boxes that I choose in which configurations that I specify later on. So there's like some alpha dependence here. And some kinematic factor that will be universal and depend on the coefficient in this case. So that's basically the schematic goal. And also some of these relations are known in the literature. What we are bringing to the picture is understanding which higher derivative corrections we can discuss on both sides. So that is as far as we see an open question. And something else we're doing is to understand what is this kinematic factor here in the case where we extend this to EFT formations. And at the same level, how do we match equations of motion in these two EFTs? Good. And in the process, we will see that these two theories happen to have like a very interesting and puzzling interplay with dimensional reduction, and to fully recent theories that are known to play a role in how string theories can fit into that picture. So many players of the game that were known before will arise in the process, but in the bottom-up process where we discuss equations of motion. Okay, so far this is quite schematic, and I'm trying to make it clearer. Something I should say is that the main method will be obvious the relation between this and this. And yeah, the relation will be that by trying to play these games where we match equations of motion, we see arising theories which precisely fall into the class of theories that can be decomposed in this. Which also, as far as we know, we still don't really understand why it happens, but it happens to be case. Okay, so now I'm going to switch to the second case, to the second point of this, which is a review of what's called covariant color kinematics of long range theory. So this is a review of some work that I found amazingly insightful of Cliff Cheng and James Magan, 2021. And the goal of this discussion is to show the part of, well, to explain what is known of these 2 points when you have no EFT deformation. So this result here, when you remove the just higher derivative, has been presented in this work. And how they proceed is as follows. So they want to map equations of motion between two theories and understand what it implies at the level of scattering amplitudes. So in order to do this, I'll just say one word about how that can be done. So how do you map equations of motion to scattering amplitudes? So let's start from the Young-Mills equations of motion, which, as I'm sure you all know, looks like this. You can introduce a source term that can be used to generate higher point correlation functions and therefore scattering amplitudes. So you can solve this thing recursively. Namely here, this thing by wisely fixing the gauge. You can extend as, for instance, box a new A plus dot. You can and you can solve, for instance, for the 1 point function of the gauge field in the presence of the source as a Taylor extension in terms of the source. And you can get this Taylor extension by writing diagrams that are Feynman-like, where you start from that source, you use Bruin propagators until you hit the source at some point, and you can stop at n sources if you're interested in n particle scattering amplitudes to get the actual scattering amplitudes at tree level. Endpoint, you're going to use the fact that this expression of the 1 point function can be differentiated with respect to the source to get endpoint correlator, and those endpoint correlators can be plugged into the LSD reduction formula to get the scattering amplitude. And schematically, this looks like this. So you're going to have the polarization tensor for the first zone, then you're going to differentiate and add the polarization tensor. And fix the source to be 0. So if you think about this in the patentable picture, that each time you do this, you're going to bring a new field down. So this whole thing is going to generate an endpoint correlator. And by removing the propagator and breaking the polarization, we're getting the scattering amplitude. Good. What Cheng and Magan realized is that this procedure is not unique. So here we've looked at this equation of motion to generate the 1 point function through a series of Feynman-like diagrams. But there are like different equations of motion that could be used before. That feels like the point that suggests different diagrams in the composition of the same answer. In particular, it happens that you can differentiate and use the Berkeley identity to get the new equation of motion for the field strength, which looks like this. This is the consequence of this Young-Mills equation of motion, but now it has a funny particularity, which is that this thing looks like box plus the box, and therefore you can use this equation of motion to get, you can invert this equation of motion iteratively and get a solution for f mu for the 1 point function of the field strength with diagrams of that sort. So you can start from, if your goal is to get the 1 point function of the field strength, you're going to invert that scalar propagator. So get some kind of scalar wave. So we are using scalar wave. Until you hit some vertex that corresponds to this. And two new f's arise that keep on propagating as scalar propagators until you hit the source. And that source is not J, the derivative of J. Okay, so that sounds like stupidly complicated with respect to this thing, but it has a very interesting. This equation of motion has a very interesting aspect, which is that you can really treat it as a scalar equation of motion. Maybe it has a scalar kinetic term here, and you can really treat those two indices as being scalar flavor indices. In the Lorentz group, or transforming the Lorentz group. Yeah, and so you can match this equation of motion to just a scalar equation of motion of a scalar that couples minimally to gluons to this kinetic term. That happens to be the theory that they wrote both. And if you take the GBES plus the GBES theory without the higher derivative corrections, and you work out the equation of motion, you're going to get something extremely similar. That looks like t squared phi plus f phi phi. So there's a mapping between the equation of motion of the field strength and the equation of motion of that scalar field. And that remark allows us to get the kind of relations that you see in Group 2. And the logic is as follows.
Sorry, what is the symmetry group of this thing?
I think it's the Lorentz group.
And where, so the Yang-Mills has some group as well, right? Where's that?
Oh, sorry, the young, good. So this table on top has two flavor indices.
Yeah.
And the other end, the big A. So the other A will be this little A that goes through without signification. And the big A is interpreted as being this mu as well. Okay, this mu is the A as a whole, so you can write that as a vector of 6 indices. These 6 indices happens to be what I'll take as big A. Good, so we are rewriting language theory in the following way. So we have some field equation for field strength that I will write about this like this. And we have, in addition, a gluon equation of motion. That's I will write like this to emphasize that it's usually the field strength, but there is a field equation of motion for potential. And so now I'm considering those two fields as being decoupled, and the fact that F is secretly the field strength of A is seen here. It's seen in the fact that they share the same source, and that by differentiating the result I get with respect to this source, I can get either a gluon field, I excite both the gluon and the field strength field. So it's a theory of the scalar and the gluon that happen to couple to the same source. And okay, that's probably quite abstract and unclear, so let me give you an example of what that implies in 3 points. So you could look at the 3-point amplitude in Young-Mills theory. So usually you just, if you use the normal equation of motion of Young-Mills theory, you have you get the you look for the 1-point function of the gauge potential, and since you want a 3-point function, you want it to hit 2 sources. So it kind of looks like this. So you're using the 3-point vertex of Young-Mills, and the 2 gluons propagate until they hit the source. Instead, we have another picture of the same exact result, which is that we start from the 1-point function of the field strength, and we wonder how can it connect itself to 2 sources leading to a 3-point amplitude. And there are 2 ways. You can either use that equation of motion, so have a scalar propagator, use that tensor, that feedback coupling, and have the the scalar is the source, in which case the source is Tj, or another way of saying this, so it's J, but that coupling here is proportional to the momentum that flows in this way. And you have another diagram that exists because of the minimal coupling that we see and the fact that the gluon is also coupled to the same source, which is the following, where you start from a field strength, you emit the gluon through the minimal coupling that hits the source. So in that case, this is not proportional to the momentum, it's just one, whereas this coupling is proportional to the momentum that flows into this coupling. So what this suggests is that the scattering amplitude in Young-Wish theory can be related to the scattering amplitude in the scalar theory by summing the three-point coupling between the three-point amplitude between three scalars and two scalars in the blue. The only thing I haven't told you is why is this one-point function related to the gluon amplitude? And the reason is that you can use as an interpolating field for the gluon either the gauge potential or the field strength. They are both equally valid interpolating field for the gluon. So in this picture, we're using the field strength as the interpolating field for the gluon. In this one, we're using the gauge potential, the gauge fixed picture. But nevertheless, we're getting a relation that looks like the scattering amplitude in Young-Wish theory of three gluons is equal to the scattering amplitudes in this theory of gauge scalar, three scalars, plus the scattering amplitudes two scalars and one gluon. The only difference is that if you were to compute this scattering amplitude, in this vertex, instead of a momentum, you just get a polarization vector for the scalar, which is 1 times something that encodes the color. So the flavor, sorry. So you would get some. So if this is the source of flavor B, and this is the scalar, you get something that's delta AB flavor. So we have to account for the fact that in this theory, we are understanding that the flavor happens to be connected to the indices of the Lorentz group, that this vertex is taken to be proportional to the momentum. And there's a clear rule that has to be followed, which is that you can just write the LSD reduction formula in that case and map what this should be and what this is actually. And you'll find that the flavor generators that appear as traces in this theory here, when the big A is taken to be an arbitrary index, have to become something a bit funky, maybe a trace of ugly thing that they shouldn't probably look at. In detail, what matters is that it's completely fixed. And this thing here comes about because we're using the field strength as an interpolating field, so we have to account for the fact that some momentum, we have to divide by some momentum to give just the gluon state, and this thing accounts for the fact that this source is hit by, has an extra power of momentum because of the way the source is coupled to the field strength. Okay, that's the picture, but so it's quite schematic at that point. But what's important is that we've artificially separated the gluon field into its field strength and some other gluon field, that the relation between the two is captured by this dependence on the same source. And from that, we can get different diagrammatic decomposition of the same physical object that give us amplitude relations. And this thing I did at 3 point, but you can do it to arbitrary multiplicity, and replacement rule is doing this in all cases. So the equation 2 here becomes that the Young-Wish amplitude of gluons becomes the sum of all GDAS amplitude where you have at least one scalar times the schematic factor. Good.
Is there also a field definition which takes you from one theory to the other, or it's just at the level of equation function?
Oh, it's at the level of the equation function, as far as you can see.
There's no like transformation which makes this manifest.
Yeah, not that we know of, yeah. Yeah. Yeah, the fact that we can use recursive indication functions that rearrange some bits and so on is important. So it's important that we're describing on-shell objects. So, which connects to the fact that these things have been observed in scattering amplitude. So any question on this? So that was a review. So what we've done actually follows very much the same pattern. Then we are going to describe a given theory in terms of a set of equations of motion that are somehow artificial, that allow us to map dynamics to dynamics of the theory of scalars coupled to gluons. So we can do it for many EFT formations. Highlight how it works for the simplest one. We just take the result. So the simplest thing you could think of if you want to deform this whole story is to do so this is the second part of EFT formations. The first thing you could think of is to add to the theory of gluons the lowest dimensional higher dimensional operator that exists, which are schematically called FQ. So this is the first EFT deformation you can think of in Lagrange theory, and the Lagrangian is the following. So the Lagrangian of Lagrange theory, and to it you add the term which is the following. So still the structure constant of the SU engage group, for instance, and some cubic coupling of H fields. Which is this. So yeah, that's the first EFT deformation you can imagine in Lagrange theory. And you could wonder, well, can the same kind of story happen? Can I map it to the theory of scalar? Can I get amplitude relations through the mapping of the equations of motion? And something that suggests that it can happen is that this theory is precisely the kind of theory that can be put in the form that I was presenting before. So this theory, this deformation is still compatible with the fact that you can write the amplitude of that theory into this decomposed form along color and kinematic numericals that obey the same algebraic relations. So yeah, that's the only logic we had when we started this whole thing. And you could ask, okay, what about the equations of motion? Does the same magic happen as we just saw before? It happens not to be the case. So if you did the same manipulation and try to write an equation of motion that looks like this graph view, you'll get the same term as before, and you get a term with 3 F's. I'm not contracting indices, but just to give you the schematic of it. And you get something else, which is this. Where the so the two terms which are here and here come from the addition of these higher dimensional operators, as you can see from just counting mass dimensions. And this thing here, because of the way the indices are open just on covariant derivatives, has no scalar equivalent. So there is no clear way in which I can reinterpret these new indices as being some open scalar index. There's no meaning to which the space-time covariant derivative can be taken in that scalar space. It doesn't seem to be the right way to go. Well, and actually the right way to go is much simpler. It's just that you can write the equation of motion in this theory, which looks like the one we know. And there's just one tiny addition to it, which is this. So here I've introduced a bit of scale. So this thing is a dimension 6 operator, so in 4 dimensions it has, there are 2 math dimensions that need to be consecutive. That's why I introduced that scale where it's new physics that generates this operator at root level, which would exist on the PM. And yeah, so the equation of motion gets modified to this times and then the magic happens again. Because if you look at that term, so now if you think about the 1 point function of the field strength, you can try to compute